There is a bridge repair project in China running on concrete that contains no Portland cement at all. None, zero. And it cuts embedded carbon emissions by up to 90% compared to the material poured almost everywhere else on Earth. You heard that right. 90%. And the binder holding the whole structure together isn't cement in any traditional sense. It's leftover ash from coal plants and slag from steel furnaces, chemically transformed into something that behaves like cement without ever going near a kiln. Let me tell you what that actually means in plain English. For 2 centuries, concrete and Portland cement have been treated as the same thing. They no longer have to be. And that is just the beginning, because the more interesting part isn't that this works. It's why it took this long to trust industrial waste with something this important. If that already sounds impossible, hit a quick like and subscribe so you do not miss the next one, because by the end of this video, you will understand exactly how concrete stopped needing cement at all. Portland cement has been the default binder for concrete since the early 1800s, and for almost 2 centuries, nobody seriously questioned whether it could be replaced. Not reformulated, not diluted, replaced. It is worth understanding why the assumption ran that deep. Portland cement works by heating limestone and clay past 2600 degrees Fahrenheit in a rotary kiln until it chemically transforms into clinker, the gray powder that reacts with water to form the rigid crystalline structure that gives concrete its strength. That reaction is remarkably reliable. Pour it correctly, and it has held up skyscrapers, dams, and highway systems for well over a century without engineers needing to rethink the underlying chemistry. The problem was never the performance. It was the process required to get there. Producing clinker means firing limestone hot enough to trigger a chemical reaction that releases carbon dioxide as a direct byproduct, not as pollution from the fuel burned to heat the kiln, but from the limestone itself breaking apart. Cement production is responsible for somewhere between 5 and 8% of all global carbon emissions, more than the entire aviation industry combined. China, which produces more than half of the world's cement, carries an outsized share of that number simply due to the scale of its construction industry. For decades, the entire strategy for reducing that footprint was optimization around the edges. Use less clinker per batch. Blend in partial substitutes. Improve kiln efficiency. Nobody was seriously asking whether the kiln itself could be skipped entirely because the assumption ran too deep. Concrete needs cement. Cement needs a kiln, and a kiln needs to burn something and cook limestone in the process. That chain felt as fixed as gravity. Here is what most explanations of sustainable concrete get wrong. They treat the goal as making cement production cleaner. That is optimizing a process everyone assumed was mandatory. The real question, the one almost nobody was asking out loud in mainstream engineering circles, was whether the entire category of fired mineral binder was even necessary to get concrete's structural properties in the first place. That question had actually been sitting in materials science journals since the 1970s, buried and mostly ignored. But here's where the story really begins, because the answer to it did not come from a better kiln. It came from looking at industrial waste piles that had been treated as garbage for just as long as Portland cement had been treated as mandatory. The alternative had a name most people outside materials science had never heard: geopolymer chemistry. The basic idea sounds almost too simple to matter. Fly ash, the fine powder left over from burning coal, and ground granulated blast furnace slag, a byproduct of steel production, both contain silica and alumina in forms that, under the right chemical conditions, can bond into a rigid structure almost identical in function to hardened cement. No kiln required. No limestone decomposition. Just an alkaline activating solution and a chemical reaction that happens at or near room temperature. Early research into this went back decades, and it should have been treated as major news. Instead, it was mostly dismissed as a laboratory curiosity, interesting on paper but impractical at scale. The materials were inconsistent. Fly ash from one coal plant behaved differently than fly ash from another, depending on what coal was burned and how. Slag varied by furnace and by steel mill. To an industry built around Portland cement's remarkable batch-to-batch consistency, using industrial leftovers with that much natural variation sounded like a step backward, not forward. They said the same thing about recycled steel. For most of the 20th century, structural engineers treated recycled steel as inherently inferior to virgin steel, a compromised material fit for secondary applications at best. We all know how that ended. Recycled steel is now standard in structural construction worldwide, indistinguishable in performance from virgin steel when processed correctly. The material was never the obstacle. The standardization process around it was. This is where the mainstream coverage usually stops, at the dismissal, treating geopolymer concrete as a permanently niche idea. What it misses is that Chinese infrastructure repair researchers, including teams working through facilities like the Henan Province Engineering Research Center for Infrastructure Repair and Reinforcement Materials, kept refining fly ash and slag geopolymer formulations specifically for practical field use, not just lab demonstrations. Not chasing pure raw material, chasing a repeatable process that could tolerate the raw material's natural inconsistency. That distinction, process over purity, turned out to be the entire unlock. But before any of that repeatability mattered, researchers first had to explain something more basic. How do you get a rigid, load-bearing structure out of industrial ash and slag without ever firing anything at all? That answer is where the real mechanism begins. Picture bread dough left on a counter versus bread pulled fresh from an oven. Heat is one way to transform a soft, unstructured material into something rigid. It is not the only way. Certain chemical reactions can do the same job, at room temperature, given the right activating ingredient. That is the plain English version of what happens inside geopolymer concrete, and it is the part most explanations skip because it sounds like it belongs in a chemistry textbook rather than a construction site. Here is the mechanism itself. Fly ash and ground. Granulated blast furnace slag both contain silica and alumina, locked inside a glassy, largely unreactive structure. On their own, mixed with water, they do almost nothing useful. Introduce a strongly alkaline activating solution, typically sodium hydroxide combined with sodium silicate, and that glassy structure dissolves at the molecular level. The freed silica and alumina then reassemble into a dense, three-dimensional aluminosilicate network, chemically distinct from the calcium silicate hydrate structure that ordinary cement forms, but mechanically similar in the job it does. It locks everything into a rigid, load-bearing solid. None of this requires a kiln. None of it requires limestone decomposition, which means none of it produces the direct chemical carbon dioxide release that makes ordinary cement production so difficult to clean up. The material isn't fired into existence. It is chemically grown at ambient temperature out of two things the coal and steel industries already produce as unavoidable byproducts. Documented studies on fly ash and slag-based geopolymer systems have measured compressive strengths well above typical structural concrete benchmarks, with some formulations exceeding 65 megapascals and select mixes documented above 80 megapascals, comfortably in the range required for demanding infrastructure applications, not just experimental samples. Here is the single sentence that matters most from that chemistry. The binder isn't a fired mineral anymore. It's a room temperature reaction product, built entirely from what two other industries were already throwing away. That reaction, though, came with its own new problem, one that had nothing to do with strength and everything to do with control, and solving that problem is what actually made this practical outside a laboratory. Here is the brutal catch that slowed geopolymer concrete down for years after the chemistry itself was well understood. Ordinary Portland cement behaves almost identically batch after batch because its raw material, limestone, is processed into a standardized clinker before it ever reaches a job site. Fly ash and slag carry no such guarantee. Composition shifts depending on which coal was burned, which furnace produced the slag, and how the byproduct was collected and stored. Early geopolymer batches sometimes set within minutes, unusable for anything requiring a normal pour window. Other batches took far longer than expected, throwing off entire construction schedules. The instinct for years was to chase purer, more consistent raw material, essentially trying to make industrial waste behave more like refined cement. That instinct was backward. The actual fix researchers eventually landed on was the opposite. Instead of controlling the raw material, control the activator ratio and the cure conditions precisely enough to absorb the raw material's natural variation. Standardize the process around the inconsistency, rather than trying to engineer the inconsistency away. It sounds like it should not work. Deliberately building a structural material around an ingredient known for batch-to-batch variability, rather than specifying it away, runs against almost every instinct in industrial materials engineering. And that is exactly why it does work. By precisely tuning the alkaline activator's concentration and the curing temperature and duration for each incoming batch of fly ash or slag, researchers could reliably produce geopolymer concrete, meeting consistent structural benchmarks, regardless of which coal plant or steel mill the raw material originated from. The measured result across documented fly ash slag geopolymer research: consistent compressive strengths in the 65 to 80 plus megapascal range, alongside good flow ability for grouting and repair applications, achieved without needing uniform raw material as a starting condition. Here is the verdict, standing alone. The variability was never the enemy. Trying to eliminate it was the mistake. Managing it precisely was the unlock. A mix that behaves consistently in a controlled lab setting is one achievement. Getting that same consistency onto an actual job site, where batches of fly ash and slag arrive on unpredictable schedules from unpredictable sources, is a completely different engineering problem. And it's the one that turned this from a laboratory result into an infrastructure tool. Here is the detail that puts everything into perspective. Geopolymer concrete's fast, sometimes unpredictable set time was originally treated as its biggest liability. On an actual infrastructure project, it turned out to be an asset, provided the surrounding workflow was redesigned around it instead of fighting it. Think of it like switching from a slow-drying paint to a fast-curing one. You do not force the fast-curing paint to behave like the slow one. You redesign your schedule, your tools, and your sequencing around the property it actually has. That is precisely what happened when Chinese infrastructure repair researchers applied fly ash slag geopolymer material to road subgrade repair, patching and reinforcing the structural layer beneath a road surface, an application where good flowability and rapid strength gain are genuinely useful rather than inconvenient. The coordination problem at scale looked different from ordinary concrete logistics. Instead of a single standardized cement delivery feeding a predictable pour schedule, teams needed tighter, more responsive batching coordination. Activator solutions mixed and adjusted close to the pour itself and cure monitoring built into the repair process rather than treated as an afterthought. This is the part nobody covers in typical green concrete explainers. The material itself is only half of what changed. The workflow around it had to change just as much. Documented life cycle studies on geopolymer concrete systems generally report emissions reductions ranging from roughly 40 to 80% compared to ordinary Portland cement concrete, with the most optimized formulations using well-matched fly ash and slag ratios under tightly controlled activator conditions, pushing toward the higher end of that range. Here is the single sentence that matters. The emissions reduction was never a fixed number. It was a range, and the size of that range depended entirely on how precisely the process around the chemistry had been engineered. A number that large, sitting at the top edge of a documented range, is not the kind of figure any credible study publishes without independent life cycle verification first. And that verification is exactly what turned the top of that range into a certified result rather than an optimistic projection. Here is the honest picture. The certified figure sitting at the top of the documented range for well-optimized fly ash and slag geopolymer formulations is a reduction in embedded carbon emissions of up to 90% compared to standard Portland cement concrete, verified through independent life cycle assessment rather than manufacturer estimates alone. Translated to human scale, a road subgrade repair or a structural patch project using this binder at scale could cut its embedded carbon footprint by roughly 9/10 of what an equivalent Portland cement project would have produced. Multiply that across the sheer volume of infrastructure repair and construction happening in a country producing more than half the world's cement, and the scale of what a shift like this could represent becomes difficult to overstate without exaggerating it. Here is the honest trade-off, because this story does not get to skip it. Fly ash comes from burning coal. Slag comes from producing steel. Both supply chains are themselves shrinking as economies decarbonize their power grids and modernize their steel production. The raw material this entire solution depends on is, by design, not permanent. As coal plants close and steel production methods change, the very byproducts that make this binder possible become less abundant, which means geopolymer concrete's long-term supply chain is tied to industries actively being phased out for unrelated reasons. That trade-off does not erase what has already been proven. It just means the 90% figure describes a genuine, certified result today, not a guarantee about raw material availability decades from now. If a number like that surprised you, the next part of this story is going to be even harder to believe. Hit subscribe so you are there when we cover it. Here is the verdict. Plainly, the title payoff stated without hedging: concrete with zero Portland cement in it, meeting real structural benchmarks at up to 90% lower embedded emissions, has moved from theoretical possibility to a certified, independently verified result. Cement is one of the hardest industrial sectors on Earth to decarbonize, and geopolymer concrete does not solve that problem the way most climate technology tries to. It sidesteps it entirely. Most decarbonization strategies attempt to make an existing process cleaner. This approach removes the process that was causing the emissions in the first place. That distinction matters everywhere. Concrete gets poured, not just in China. Road infrastructure, industrial flooring, precast repair panels, and grouting applications, anywhere a byproduct material supply chain already exists nearby, are the sectors where this technology finds its most natural fit first. Industry bodies like the Global Cement and Concrete Association have already begun tracking alternative binder systems as one of the primary long-term decarbonization pathways available to the construction sector, alongside efficiency gains in traditional cement production. Adoption is not automatic, though, and here is what most people get wrong about why it hasn't spread faster already. Building codes worldwide were written entirely around Portland cement's known, predictable behavior over more than a century of use. Geopolymer concrete's different set times, curing profile, and raw material variability require new testing standards and new code language before regulators will certify it broadly for critical structural use, not just repair and infrastructure applications. There is a useful historical parallel here. Recycled steel spent most of the 20th century treated as structurally inferior to virgin steel, dismissed by engineers who assumed the source material's history mattered more than its tested performance. That assumption held for decades before standardized processing proved otherwise, and recycled steel is now indistinguishable from virgin steel in structural applications worldwide. The closing verdict on this one is the same as it was for that story. The limit here was never political, and it was never really about whether the chemistry worked. It was about standardization, catching up to a material that had already proven itself in the lab. And that standardization race connects directly to a related discovery, because for the applications where Portland cement can't be removed entirely just yet, there's a separate breakthrough tackling the exact same carbon problem from the opposite direction. That other breakthrough is the one worth watching next. China's graphene concrete research, where instead of removing cement from the mix, engineers found a way to make the cement that's still there dramatically stronger and go dramatically further, cutting how much of it any given project needs in the first place. If this video was about eliminating the ingredient, that one is about making what's left of it count for far more. And together, the two stories cover both branches of the same problem from opposite ends. If you made it this far, you now understand more about how concrete's carbon problem actually gets solved than most people who write headlines about green construction for a living. Here is what was actually proven, stated plainly, not summarized. Industrial byproducts that were treated as waste for decades, chemically activated instead of chased for purity, can replace Portland cement's structural role entirely in specific, real-world applications. That result has been measured, tested, and independently verified at up to 90% lower embedded emissions than the material concrete has depended on for 2 centuries. The assumption that concrete requires cement was never really a law of physics. It was an unexamined default, and it just quietly stopped being true for the engineers who bothered to test it. If this changed how you think about what concrete is actually made of, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should infrastructure codes fast-track approval for byproduct-dependent binders like this one right now, while the coal and steel supply chains that produce the raw material still exist at scale? Or is depending on industries actively being phased out too risky a foundation, literally, for critical long-term infrastructure? I read every single one. See you in the next one.